So Unit 5 has to do all about reaction rates and kinetics. You can pause this and read through those. Here's one type of problem that you could see relating to 5.1, where it says, what is the rate of disappearance of Br in experiment 2? Well, the rate is measured in the appearance of Br2. So experiment 2, we're going to look at this rate. So 1.6 times 10 to the negative third. And all we need to do is a stoich problem. We need to convert our moles of Br2 to moles of bromine ion. To get our conversion, we look at our mole to mole ratio and then multiply and divide. So you're going to try this one on your own, restart when you're done. So for this one, you should have gotten the same 3.2 times 10 to the negative third because it's a 3:3 ratio of bromine to water. So you can read through those. The three reaction orders that you need to be able to recognize are 0, 1st, and 2nd. 0 order is the change in concentration has no effect on the rate. So if you double the concentration, rate's going to stay the same. 1st order, the concentration and rate are directly related. Double the concentration, double the rate. Half the concentration, half the rate. And then 2nd order, doubling the concentration will be 4 times the rate. Tripling the concentration, 9 times the rate. Because it'll be whatever squared is equal to your new rate. You can solve these problems one of two ways, depending on if it's multiple choice or free response. If it's multiple choice, then you don't have to show all the work. I'm trying to find the order of A. So I need B and C to be constant and A to be changing. So in experiments 3 and 4, my B and C are constant and my A doubled. And then my rate went from 0.02 to 0.08, so that's times 4. So basically I get 2x is equal to 4, so x is equal to 2. So A has the order of 2. Then, if I want to solve for B, I'm going to say, well, 1 and 3 are held constant for A and C, and B doubled, and the rate doubled. So N has to equal 1. And then for my last one, these two were doubled while these were held constant, and my rate stayed constant. So 2m is equal to 1, so m has to equal 0. So my rate law is rate is equal to k, and then brackets a to the 2nd, b to the 1st, and then I don't need to write c. If I wrote c, I would need to put it to the 0 order, but anything to the 0 order is 1. So I can just leave that off my rate law, and I get this. The other way of solving this would have been if it was free response, and we'll see that one in a few minutes. Next, it wants to know what the value of k is. So we need to pick one experiment and then plug everything into our rate law that we wrote a second ago. So I'm going to use experiment 1. So k is equal to 10. So my units on k are going to be based on the overall order. my overall order is my orders added up. So in this case, 2 plus 1 gives me an overall order of 3. If my overall order is 0, my units are going to be molarity over time. And my time is whatever it is in the chart, in this case seconds. First order is 1 over time. Second order, 1 over molarity times time. Third order is 1 over molarity squared times time. Fourth order would be 1 over molarity cubed times time. So overall order minus 1 gives you how many molarities you're going to have. So since this is third order, it's going to be 1 over molarity squared times seconds. Go ahead and pause the video and try these two on your own. Restart when you're done. So remember, it says rate of disappearance. So we've got to look in the rate column. And we're just changing it from rate of formation to rate of disappearance. So for the first one, we are converting D to A. So you should have just gotten the same answer, 0.01 molarity of A per second. Technically, it is a decrease of 0.01 molarity of A per second. And this one is a 1 to 2 ratio, so it's going to be decreasing twice as fast as A. So negative 0.02 molarity of B per second. So this one was from 2003, and we needed to figure out the orders of each reactant, just like we did a minute ago. So first, I'm going to write the rate law and put orders for each of them. So my general rate law is going to be rate equals K, BR negative to the N, H plus to the P. So that's my general rate law. Now I'm going to pick two experiments just like we did a minute ago. So I'm trying to get N to change and M and P to stay constant. So I'm going to use experiments 1 and 2. And these are held constant and these are changing. So to show that, I'm going to do experiment 2 over experiment 1. I'm doing 2 over 1 because I like to use the bigger over the smaller, so my numbers come out cleaner. I'm just going to plug everything in experiment 2 into my rate law. So for experiment 2, my rate, I don't know K, I know my BR concentration. And I'm going to plug everything into experiment 1. Now I'm going to cancel the things that were the same. And so I get 2 is equal to 2N. So N is equal to 1. It's the same thing as what I was doing before, except I need to show a little bit more work on why 2 is equal to 2N. Because I'm not explaining it in words, I'm going to do it mathematically. I could do it in words, but I would have to explain exactly which experiments I was using, who was being held constant, what was changing, and how it was changing. Or I can show it this way in numbers. So I know that for bromine, my order is 1. Now, go ahead and do M and P on your own. Restart when you have M done. So for M, I got 1 as well. You can fast forward, or you can see how I did that one. I used experiments 3 and 1. Because these are held constant, these are held constant, and then these are changing. And experiment 3 is bigger, so I put experiment 3 on top and experiment 1 on bottom. In this case, I left my N, M, and P's in there, but technically I could fill in my N's with 1s because I know what those are at this point. Sometimes you have to fill them in to solve the problem. But in this case, I didn't, since they're going to cancel, cancel, cancel. I get 1.5 is equal to 1.5 M, so M is equal to 1. Okay, go ahead and finish P if you haven't already. Restart when you're done with P. And I couldn't see any that had N and M being held constant, so I just did experiment 4 over experiment 1. My BRs are held constant, and my bromates and hydrogens are changing, but I know what my orders are for each of them, so at this point it doesn't matter. I don't have to have any of them being held constant. So solving this, my K's cancel and my bromine ions cancel. And then that divided by that is going to give me 12. That divided by that gives me 3, and that's 2p. So first I'm going to divide by 3, so I get 4 is equal to 2p. So then p is equal to 2. So now, determine your rate law and figure out your rate constant. Restart when you're done with B and C. So my rate law is what I've been writing. The only difference is instead of M, N, and P, I'm going to plug in what my values are. Make sure that you have charges on the things that should have charges. For your rate constant, you could have picked any experiment. I just used this first one. So when I solved for it, I got 5,000. My overall order is 4th order, so 4 to minus 1 is 3, so molarity cubed times seconds. For D and E, we have an electrochemical cell. We talk about how to calculate E cell in Unit 9. So let's see how to calculate our cell potential. We have Br ion as a reactant. We have Br ion as a product. So this one's going to have to be reversed. Because they gave us the reaction, we have to look at the reaction to calculate our E. We would actually reverse that one if we were trying to get it to be thermodynamically favorable, since we reversed the less positive. And then BrO3 negative is a reactant, and here it's a reactant. So for our E cell, it's 1.52 plus negative 1.065. We don't have to worry about multiplying because our E cells are not multiplied. And so that gives us negative 0.46 volts. So then the last one wants to know how many electrons are transferred. And this one's actually a super tricky question because we've got to look at the overall equation. Otherwise, we would have just said, well, 2 and 5, the common denominator is 10, so there's 10 electrons transferred. But that's actually not the right answer in this problem. If we look at it, our waters and the overall balanced equation is equal to what we see here. And we have 1 BrO3, 1 BrO3, so the actual electrons transferred is 5. But to see how we got that, because 2 is not divisible by 5, so how did we get 5 electrons transferred and not 10? So to do that, we would need to write our balanced equations and add them up. So here we need to multiply by 5 and multiply by 2 and reverse that top equation. And then combine like terms. These two actually combine to give me 6 Br2s. Everything is divisible by 2 because we had Br2 in both spots. Since everything's divisible by 2, we can't have this as our overall balanced equation because it's got to be in lowest numbers. So dividing everything by 2 will give me 5 electrons on each side being transferred. So that's how we get 5 electrons as being the final answer. Go ahead and pause and read through these. So previously we were looking at concentration and rate. Now we're going to be looking at concentration versus time. So if they say anything about how long does it take, we need to be thinking about the integrated rate law. So first order integrated rate law, concentration versus time will look like this. This is a classic half-life graph. Notice it keeps going down by 1/2. This one is 1, 2, 3. So our half-life must be whatever unit this is in, 1 hour, 1 minute, 1 second. The only half-life equation that's given on the AP test, which is the only one that you need to know, is first order. And that's 1 half-life, or half-life time, is equal to 0.693 over K. So if you know the half-life time, you can solve for K and vice versa. Here we can see that half-life graph again. We have 0.2, 0.1, 0.05. So my first half-life was 7 seconds. My second half-life is 14 seconds. My third half-life, another 7 seconds, so 21 seconds. So every 7 seconds, this is getting cut in half by 1/2. So that's one way that you know that it's something is first order, is half-life is constant. It's the only order that has a constant half-life. So that's one way that you can justify a reaction as half or first order is based on its constant half-life. If it's going down by 1/2 at the same amount of time. If we graph concentration versus time, this is the graph that's going to look like. But if we graph ln of concentration versus time, then it's going to give us a straight line. So ln of concentration versus time is first order. My slope is equal to -k, and the y-intercept is equal to ln of initial concentration. So this is your first order half-life. It's a little rearranged from what the formula chart gives you because this is in y equals mx plus b format. So go ahead and pause the video and try that first one on your own. Restart when you're done. So they gave you the half-life and they want to know the rate constant, and they told you it was first order. So that's the equation you should have used. So 0.693 over 20 gives us that. Since it's first order, 1 minus 1 is no molarities, so our unit is 1 over minutes, or 1 over time. To solve part B, I can use the integrated rate law, and I can also use the half-life equation. The half-life equation, I would say 0 half-lives, I have 100% left. After 1 half-life, I would have 50% left. After 2 half-lives, I would have 25% left. Well, this reaction is 75% complete, which means I have 25% left. So 2 half-lives have gone by. 2 half-lives times 20 minutes means 40 minutes must have been required. So that's solving it. Knowing the half-life, we can set up a table like so. We also can solve it using the integrated rate law. We would have to use it with the integrated rate law if the numbers weren't as clean. Maybe it was 71% or 67%. So for the integrated rate law, that's my equation. I want 25% left. I know what my K is because I solved for it in the previous problem. My time is what I'm looking for. And if I'm dealing with percent, I'm starting with 100%. So ln 25 minus ln 100 divided by negative 0.0347 gives me 40 minutes. Here we're given some concentrations and times. So first it wants you to find K, and they tell you that it's first order. Go ahead and pause and solve for this one. Restart when you're done. So they have time, so we know we're using integrated rate law. I'm going to use that first and third one. So my final concentration is 1.2. It took 10 minutes to solve for it. And my initial concentration is 2. So just like a second ago, we can subtract ln of 2, divide by negative 10, and our K value is 0.051. My units, 1 over minutes. If you haven't already solved number 2, go ahead and solve that one. So now you're looking for the final concentration. We know what K is. There's 12 minutes. Make sure that your units always match. Had this said 120 seconds, we would have needed to convert that to minutes. And my initial concentration is still 2. So solving everything on the right, I get ln of concentration is equal to 0.0811. And then the opposite of ln is raising it to the power of e. So concentration is e to the 0.0811, which is 1.08. For second order, when you graph 1 over concentration versus time, it's going to give you a straight line. Notice that your slope is positive, so slope is equal to K. This is our integrated rate law for second order. Again, notice the positive KT. And then zero order is when you graph concentration versus time and it gives you a straight line. Again, it has a negative slope, so slope is equal to negative K. And this is the zero order integrated rate law. Sometimes you're just given the graphs like this one and asked what order is this reaction. So pay attention to your units on the y-axis. In this case, the straightest line was this one, and 1 over concentration is second order. So if we were explained, we would say the graph of 1 over concentration versus time gave the straightest line. So that corresponds to second order. So how can you find K? We would find the slope, and slope would equal K. So if these numbers were a little bit clearer, we could find our two numbers, do y2 minus y1 over x2 minus x1. You can pause and read about elementary steps. So this one wants you to write the rate law from the elementary step below. You can only write a rate law from an elementary step. You cannot write a rate law from a given balanced overall equation. So to write a rate law from an elementary step, you're just going to have rate equals K, because that's always there. And then we're just going to look at the reactants. And the orders are the coefficients. So we have NO to the second and Cl2 to the first. So on this one, they gave us the overall equation. Wants to know what's the equation for step 1. So first, find your equation for step 1. Restart when you're done. Well, working backwards, I have a D and a D. So D is going to be from step 2. We have 3 C's, 3 C's. We don't have a Y in the overall equation, so Y must be a product, so that way it'll cancel out. We have 2 A's, so we must have an A on this side to give us 2 A's, and there must be a B as well. So notice 2 A's will give me 2A, B gives me B, and then my Y's would cancel out. So the equation is A plus B yields Y. So then my rate law, we're going to be seeing a little bit more on mechanisms in a minute, but we look at the slow step and anything before the slow step. Since our first step is the slow step, we can write the rate law based on the molecularity of the first step. So we have rate equals K, we have 1A and 1B as reactants, and so that's my rate law. Go ahead and pause and read through the collision model. Some important takeaways is effective collisions. If you're having to explain how does rate increase or decrease, or how can you increase the rate, these are the 2 things that you should be referencing. In order for a collision to be effective, you need 2 things. The reactants have to collide with sufficient energy to overcome activation energy. And the molecules have to collide in the right orientation to produce a reaction. So some ways that we can change those: temperature will increase the number of collisions. If there's more collisions, there's going to be a greater chance they collide in the right orientation. And also, temperature will increase the force of collisions. So there's a greater chance they're going to collide with the required activation energy. Temperature affects both things. It's the only one that affects both of the things needed for an effective collision. Concentration just increases the number of collisions, so greater chance they collide in the right orientation. Surface area, we want to break up a particle. So smaller pieces have a greater surface area. So greater chance that the reactants will collide in the right orientation because now they're spread out. There's more area for it to react with. Previously, it could only react with the outside. Stirring increases our number of collisions, so greater chance they collide in the right orientation. And a catalyst provides a pathway with a lower activation energy. So more molecules will have the required activation energy when they collide. In order for molecules to collide in the right orientation, here we have unimolecular, bimolecular, and termomolecular reactions. Unimolecular means you have one reactant and it's basically just breaking down. Bimolecular, we're going to have 2 reactants hitting each other, and termomolecular, 3 reactants. The likelihood of 3 reactants all hitting each other in the right orientation, all with the correct or required activation energy when they collide, isn't as likely as bimolecular or unimolecular. And that's why you don't have 4 reactants hit each other, because that would be even less likely. Here's our max Boltzmann distribution. We've seen a couple of times now. And it says which one is high temperature, low temperature. Remember, the higher the temperature, the further to the right it is and the further down it is, because you're going to have a greater distribution of molecules with different kinetic energies. But over here is activation energy. The higher temp, more molecules have the required activation energy than these do, because very few molecules have that much kinetic energy at the low temp. You can read through those about energy profiles. So pause and figure out which two diagrams could represent the same reaction, one catalyzed, one uncatalyzed. If you said 1 and 2, you are correct. Make sure you know the reason why as well. They're the only ones that have the same reactant and product potential energy. If you're only changing where one has a catalyst and one doesn't, the only thing changing should be the activation energy, not where they're starting or ending. So of diagram 1 and 2, which one is catalyzed? If you said 1, because it has a lower activation energy, you are correct. So activation energy is from where you start to the top of the hill. So go ahead and pause and answer these three. Here's my reactants, here's my products. It's released energy, so it must be exothermic. Delta H is products minus reactants. So A is the difference of where my products end and my reactants start. C also is where my products are to my reactants are pretty close to it. So C is also a pretty good answer. It looks like it may be a little bit less or a little bit lower down. So A or C. Activation energy should have been from where you started to the top of the hill. So you're starting here, top of the hill is B. So B is activation energy. If it said activation energy of the reverse reaction, we would have been starting here at the products and going to the top. So that would have been B plus C. So going to read through about mechanisms. So in order for a mechanism to be possible, the elementary steps have to add up to the overall balanced equation, and the rate law has to be consistent with the experimental rate law. So intermediates are made in one step and used up in a following step. So I would cross out X, I would cross out Y, and that's all I would cross out. So X and Y must be intermediates. Notice they're formed and then used, formed and then used. You can read through those. And then pause the video and solve A and B. So we're going to cross out everything that's the same. So NO2, we made it and then used it, so that's an intermediate. A catalyst we're going to start with and then end with, so that's NO. So make sure you know the difference between intermediate and catalyst. So intermediate is a product and then reactant, while a catalyst is a reactant then product. It says, which is our rate determining step? Our rate determining step is the slow step, so that would be our first step. How many times was each reactant used in the rate determining step? Well, only once. And so to write our rate law for our reaction, remember that we're going to look at our reactants of our slow step. So rate is equal to K O3 NO. So you can have a catalyst in your rate law. You cannot have an intermediate in your rate law. So let's go ahead and write some more rate laws for mechanisms. In this case, your first step is not going to be the slow step. So there's two ways of doing it. So first, we're going to cross out our intermediates. And then we look at the slow step and anything that occurred before the slow step. And I'm going to look at the reactants of those. So I'm going to look at both reactants that I have left because my slow step was the second step. So rate is equal to K NO squared and then BR's like so. So that's my rate law. That works most of the time. There's a few instances where it wouldn't. If it didn't, you would have to do it this other way. So we would write the rate law for the second one, because that's my slow step. But notice I have an intermediate. I can't have an intermediate, so I'm going to look at the first one, and I'm going to say this is equal to rate equals K2, because that's my second step. So step 1, I'm going to have K to the NO BR2 is equal to K negative 1, the reverse reaction, NOBR2. Rearranging and solving for just my intermediate. Now I can plug this into my first equation for that intermediate. So I get rate is equal to K2 K1 over K negative 1. And so notice I have 2 NOs and 1 BR2. And then my K, this is just K, or K prime, and K prime is technically made up of K2 times K1 over K negative 1. So notice we get the same answer regardless. Just one way was much quicker, but it doesn't work 100% of the time. It does work probably at least 95% of the time, but it doesn't work 100% of the time. If you got confused there, you can also watch the daily videos on AP Classroom. Here's one more. So what is the rate law for this above mechanism? So we'll do it the long way and the short way. So that was your slow step. So cancel, cancel. So that's my answer. I have HBr squared times O2. If I was to do it the long way, so to write the rate law for the second equation, which is my slow step, rate is equal to K2 and then for my first step, I have K1 is equal to HBr times O2, K negative 1, HOOBR. Rearranging for my intermediate, and then plugging it all in. I get the same rate law. K prime being K2 times K1 over K negative 1. Go ahead and read through those. So how many elementary steps does this reaction have? Well, every hump is an elementary step activation energy. Since there's 2 humps, there must be 2 elementary steps. The rate determining step is going to have the largest activation energy generally. And the first step has the largest activation energy. So step 1 is the slow step. And then the overall reaction, lost energy, so is exothermic. Notice the first step is endothermic, and then the second step is largely exothermic. But overall, exothermic. Go ahead and pause and do this one. Restart when you're done. So you should have said 3 elementary steps. We have 3 humps. The rate determining step, we still have the largest difference for the first step. So the first step is going to be our slow step. It's got the largest activation energy. And then the overall reaction is also exothermic. So go ahead and read about catalysts on this page. Restart when you're done. So we've already touched this on a previous slide, but remember that catalysts speed up a reaction by providing an alternate pathway with a lower activation energy. So given this mechanism, what is the intermediate and what is the catalyst? You said Y is the intermediate and X is the catalyst. You are correct. So let's talk about some different types of catalysts. In acid-base catalysts, a reactant either gains or loses a proton, and that changes the rate of the reaction. In other words, the reaction is performed in an acidic or basic solution, but the acid or base is not used up. We also have surface catalysts, where either a new reaction intermediate is formed or the probability of successful collisions is modified by providing a surface for the reaction to occur on. So in a catalytic converter, it's going to use platinum or palladium to cause unburned hydrocarbons to stick to the metal where it can react with the oxygen. Otherwise, the gas is going through so quickly that it's not able to react. We also have enzymes that can accelerate reactions by binding to the reactants in a way that lowers the activation energy. Other enzymes react with reactant species to form new reaction intermediates. The issue with enzymes are they're specific to a compound and usually have to have a gentler condition, such as lower temps. For example, sugar will not burn until high temperatures, but inside the body, sugar can undergo the same combustion reaction at normal body temperatures because of enzymes. Here we have a plot of ln of concentration versus time, which means it's first order, which you should be able to recognize. It says draw a line for an approximation of the plot if a presence of a catalyst was there. So if a catalyst is there, it's going to speed up the reaction. We have time on the x-axis. We should start and end at the same amounts. It should just take us less time to reach it. So something like that. And finally, pause the video and answer these 4 questions. Restart when you're done. So if you are adding a catalyst, you should start and end at the same spots. It's just going to have a lower hump because it has a lower activation energy. So it says label the activation energy for the catalyzed reaction. So from where you start to the top of the hill is activation energy. And then from where I start to where I end is delta H, or the overall change in energy. Notice it didn't have a large change, but it is endothermic because it gained energy. And then it says, explain why the presence of a catalyst increases reaction rate. Well, as we can see from the picture, now the molecules don't have to go to the very, very top. They can take this shortcut, which requires less activation energy. So a catalyst provides an alternate pathway with a lower activation energy, so more collisions will have the required activation energy to react.